All right, let's get right into it. We're looking at a pretty fascinating new training method from Google, and it might just fix one of the biggest, most fundamental problems with today's AI. It's a technique that could, well, teach an AI to actually think before it speaks.
And this really gets at a strange paradox, doesn't it? I mean, you have these incredible AIs that can write beautiful poetry, they can whip up complex code, they can even pass a medical exam. But then you ask one to follow a simple multi-step plan or solve a puzzle that requires a bit of foresight, and they just fall apart. So, what on earth is going on?
To figure that out, we've got to look at this massive blind spot that even the smartest AIs have. And it all comes down to the way we've been teaching them to learn in the first place. So the vast majority of large language models, LLMs, are trained using a method called next token prediction. And it's pretty much exactly what it sounds like. The model sees a sequence of text, and its only job, its entire world, is to guess the very next word or token. It does this billions upon billions of times, and that's how it gets so good at grammar, remembering facts, and even mimicking writing styles.
But, see, that creates a huge problem. This whole approach is incredibly short-sighted. Imagine you're trying to get through a complex maze, but the only thing you can do is look at the single paving stone right in front of your feet. Sure, you might take the next step correctly, but you have no high-level plan, right? No sense of the overall map. You're almost guaranteed to get lost. And this isn't just some abstract idea. The researchers at Google actually did the math. For tasks where you only find out if you succeeded at the very end, what's called a sparse reward problem, the odds of an AI stumbling upon the correct multi-step solution just by guessing one word at a time is, get this, 1 in a million. It's just not going to happen. It's an awful way to learn complex tasks.
Okay, so if training the model from the outside in just isn't working for these kinds of problems, where do you even look for a solution? Well, the Google team had this brilliant insight. What if the answer wasn't outside at all? What if it was already inside the model the whole time? And this right here is the big aha moment. The researchers realized that these models, the ones that build their answers one piece at a time, they've already learned all the building blocks for complex behavior. It's all in there from their massive pre-training. The ability to plan isn't missing. It's just buried. It's hidden. And the current training methods just can't get to it. So where is this hidden knowledge? It lives in a place called the residual stream. Now, the easiest way to think about this is like the model's internal workspace, or maybe its stream of consciousness. It's the river of calculations and signals flowing between all the layers of the neural network. This is where the AI is actually thinking, long before it ever spits out a single word. So to tap into this hidden potential, the researchers came up with a really clever new component. So let's meet the hero of this story, the metacontroller. The metacontroller is basically a smaller, separate neural network that works inside the main AI. But here's the really key difference. It doesn't write any of the output. Its only job is to be a manager for the AI's thought process. It watches that internal chatter and just gently nudges it in a more useful direction. So how does it do that? Okay, 3 simple steps. First, the metacontroller just reads the AI's internal state, that residual stream we were just talking about. Second, instead of trying to pick the next word, it just nudges the internal signals toward a high-level goal, something abstract like head towards the red square. And then third, it just gets out of the way and lets the big, powerful, pre-trained model do what it's already great at, figuring out the tiny details like, okay, now activate the leg joints to actually move. Now this diagram is really cool because it shows you exactly where the magic is happening. See? The metacontroller isn't at the start or the end. It's jumping in right in the middle layers of the main model, steering that flow of information to keep it aligned with the long-term plan. It's a guide, not a dictator. Okay, so the theory sounds great, but does it actually work? The researchers set up some really tough challenges to see if this new method, which they call internal reinforcement learning, could pull off what other methods couldn't. And this was the test bed. They took a simulated 4-legged robot, an ant, and gave it a really tricky job. It had to navigate a complex space and reach a series of colored squares in a very specific order. And here's the kicker. The AI only got a reward at the very, very end, and only if it did the whole sequence perfectly. This is that classic sparse reward problem that is just a nightmare for standard AI. And the results? I mean, they were just night and day. After 1 million attempts, the standard AI training methods had learned basically nothing. They just couldn't solve it. But the model that was guided by internal RL,
It achieved a really high success rate and in way, way fewer tries. It wasn't even close. But here is the most crucial detail of all. The very best performance came when the researchers froze the big, pre-trained AI model. They didn't let it learn or change at all, and they only trained the tiny metacontroller. This was the smoking gun. It proved their hypothesis was right all along. All the skills were already there, baked into the big model. It just needed that little manager to learn how to unlock them and conduct the orchestra. So, what does this all mean for the future of AI? This isn't just some clever lab experiment. This could be a really fundamental shift in how we build and train intelligent systems. Right now, if we want an AI to reason through a problem, we make it use something like chain of thought, where it has to literally write out every single step. That's external reasoning. This new approach unlocks internal reasoning. The AI can think through the high-level plan efficiently, inside its own head, so to speak, before it gives you a much more direct and coherent answer. The applications for this are just huge. Think about it. More reliable, autonomous agents that don't get easily distracted. Robots that can actually perform complex, multi-step tasks in the real world. AI that can generate massive, complex software by planning out the architecture internally first. This could be a game changer for any field that needs real, long-term planning. And that kind of leaves us with this one big, provocative question. For years, we've been totally focused on what AIs say, their output. But this research forces us to look at their internal process. So what happens when an AI doesn't just need to talk its way through a problem, but can finally, truly think it through?